Hey everyone, when we last left off, we introduced energy, and I want to continue that discussion. So, energy is how change takes place, how work is done. And we can convert from potential to kinetic energy. So, here is a diver. That diver is up above the water. They have a lot of potential energy, more than the people down here in the water. When they jump off the diving board, they convert potential to kinetic energy, the energy of motion. And when they hit the water, they now have less potential energy than the people on the platform. But you can convert again. You can climb back out. You're going to take the stored energy in your body and convert it to potential energy. So you're going to climb, and then you have more potential energy again when you're up on top. You have more than the people in the water. So climbing converts the kinetic energy of muscle movement back to potential energy. So you can go from one form to another. This brings up the laws of thermodynamics. We're going to talk about the first and second law. The first law of thermodynamics. Energy cannot be created or destroyed, but it can be transferred. Okay, it can go from one place to another. This is known as the conservation of energy. So, from the time of the Big Bang, all the energy in the universe existed. And there's no more being made, okay? Just the amount that's here in the universe. And some of that energy is nicely ordered, like this molecule of gasoline. It's easy to get at and use. And so this gasoline can be put in a car, and that energy can be transferred from potential to kinetic, the energy of motion. Okay? Second law of thermodynamics. If energy is transferred or transmitted, so if you go from gas to moving your car, some of it is lost. Okay, some of it will be lost, usually as heat. What do I mean by lost? It means heat is the random motion of particles, and as heat spreads out in the universe, it's no longer usable for any work. It's disordered. It's unusable for work, and so it's said to be lost. It's not destroyed. It's just unusable, right? And fancy word for that, the random motion of particles, is entropy, chaos. With every transformation of energy from one form to another, energy is lost and entropy increases. And if you want to expand this out to the universe, entropy increases in the universe every time a reaction takes place. And one prediction is that one day there will be no more usable energy left in the universe, and we'll die a cold, cold heat death. They call it the heat death of the universe, when all the energy is spread out through space. So in what form is energy lost? I hope you remember that. It's lost typically as heat. Now, in a closed system, entropy increases every time energy changes until all energy is lost. For example, if you have a jar with a mouse in it, I'm not going to draw a very good. There's our little mouse. There's his ears. All right. There's a jar with a mouse, maybe a little bit of food in there. That mouse is going to eat the food and make it part of the mouse or whatever. But eventually, it runs out of food. All energy has been converted, and everything in the jar dies. Right? All energy is lost. But the sun. So you might think that the Earth would have the same problem. Here's the Earth. Let's just draw a continent on here. Oh, maybe not. There's a continent. All right. So there's the Earth. Lots of chemical reactions happening. How can evolution happen? How can organisms live if energy is lost all the time? How can things get more complicated? Well, we have about 8 light minutes from Earth, the sun. Here's the sun shining brand new energy at us every day. So the Earth itself is not a closed system. We have new energy coming in all the time. The universe as a whole, however, is a closed system. There is no new energy coming into the universe. Eventually, all the energy in the universe will be unusable for work. All right. Now, things to think about. When we have things that are nicely structured, like this wall, they have high potential energy. Just like when we have a high concentration of chemicals, or like we'll talk about this when we talk about diffusion later. That's a high concentration of something. They have high potential energy. Think about it this way: if this brick fell out of the wall all the way to the ground, it would hurt when it hit you. There's a lot of potential energy in this wall. Things that are spread out or chaotic have low potential energy, but you can go from this form to this form. You can do that, right? For a wall to fall down is just natural. That's going to happen all on its own. That's going to be spontaneous. That means eventually that wall will fall. It might not be fast. It's not instantaneous, but it's spontaneous. Now, bricks will not build themselves up into a wall, but you can build a wall out of bricks if you apply some energy. You can go the other way if you add energy. So you can go from low to high. You're like you're investing energy in those bricks to build that wall. So we can see in a bear eating a fish, lots of molecules in that fish. It's kind of like a nice brick wall, right? Lots of energy, lots of chemicals, lots of things that bear can eat. That's chemical energy for the bear. So energy can be transferred, the first law of thermodynamics. Now when that bear is transferring that energy and utilizing it, a lot of it is going to be lost as heat, and these chemicals are being released. This is the second law of thermodynamics. And that brings us to a really important idea, is that energy flows through an ecosystem. It comes in as light. What do we mean by that? Well, this fish ate bugs. Those bugs ate plants. Those plants received sunlight energy, and that's how that energy got into the ecosystem. So energy flows into an ecosystem as light, and it leaves as heat. It radiates off into space and is gone forever. That brings us to the topic of free energy, and that'll be where we pick up in the next video.